In our previous video, we talked about how services have port numbers that they use so that other devices can communicate and use those services. We refer to these as well-known port numbers because both the server and the client need to know exactly what port number they'll use to communicate. This is not only important for the server and the client, but it's also important for any firewalls that may be in the middle of that communication. Firewalls have to decide whether to allow or disallow this traffic, and they often make that decision based on the port number. As we go through this video, you'll see that there are a lot of different port numbers that you should use. And if you've never worked with port numbers before, this will seem like rote memorization. But the port numbers themselves become easier and easier to remember as you continue to use them. It's important to know these port numbers and what protocols are often used by a particular port number, but it's also important to know when you would use these protocols. For example, your exam might ask you what port number is used by an application that transfers data in a particular way across the network. Let's start our conversation of port numbers with FTP, or the File Transfer Protocol. As the name implies, this is a protocol that transfers files from one device to another. There are two port numbers used by FTP. One is TCP port 20. This is for data transfers, and TCP port 21, which is used to control the data transfer. FTP is a generic way to transfer data between devices, but it commonly requires some type of authentication to log into that remote device. So you might use a username and password, although some systems will allow you to log in as anonymous and use any password to gain access. The FTP protocol also includes a number of file management functions. So when you connect to an FTP server, you can list all of the files on that server. You can add, delete, rename, and perform other file management functions, all by using FTP. There may be times when you need to connect to a remote device through a terminal or command line front end. It's common to use Secure Shell, or SSH, to provide this terminal connection to a remote device. SSH commonly communicates over TCP using port 22, and it has this text-based front end to be able to access that remote device. Although we see plain text on our screen, any communication sent over the network is sent as encrypted data. That's where the secure comes from in the name Secure Shell. There's another way to connect to a remote device using this text-based or console front end, and it's using Telnet, or the Telecommunication Network Protocol. Telnet commonly uses TCP port 23 to provide this connection. Just like SSH, Telnet provides this text-based front end that allows us to connect to the remote console of another device. But unlike SSH, all of the communication between this Telnet front end and the Telnet server is all sent in the clear, or non-encrypted. This means that anyone who might be capturing packets between these two devices will see everything that you're sending over this link, including usernames, passwords, and everything else. This is why we often say that you shouldn't use Telnet on your production networks, and instead you should always use SSH for terminal communication. There are probably millions of email servers that are located on the internet, and the protocol that those email servers use to communicate with each other is the Simple Mail Transfer Protocol, or SMTP. SMTP commonly uses TCP using port 25. Not only is SMTP used to communicate between mail servers, but it's also used for our mail clients to send mail to a mail server. So if you're using a mail client on your mobile device or your desktop computer and you're sending an email message, you could be using SMTP. Although it's common to use SMTP to send mail, receiving Receiving mail is done using a completely different set of protocols. So if you were to look at your email client, you're probably using IMAP or POP3 to be able to receive mail and SMTP to be able to send mail. If you need to connect to a remote website, you would probably type into your browser www.professormesser.com and hit enter. Behind the scenes, your system needs to be able to communicate with the Professor Messer web server, but it has no idea what the IP address is for that server. To be able to resolve an IP address from that fully qualified domain name, your system will use DNS, or the Domain Name System. DNS commonly uses UDP port 53 to be able to make this connection between you and the DNS server. These are obviously very critical resources because we don't often memorize IP addresses of servers, and very often server IP addresses can change without any type of notification. It's DNS that provides that resolution between a name that we're typing in on the browser and the IP address that will be used for the actual communication. If you've ever used your mobile device on the Wi-Fi network of a coffee shop, then you've automatically received an IP address that you can use on that network. This IP address was assigned automatically using the Dynamic Host Configuration Protocol, or DHCP. The well-known ports for DHCP are UDP port 67 and UDP port 68. Of course, you need a DHCP server to assign these IP addresses to devices on your network. That functionality is commonly built into the routers and wireless access points that we use these days. This DHCP server will have a large pool of IP addresses that can then be assigned to devices on your network. All of these IP addresses are assigned in real time. So when you start up your computer, it queries the DHCP server, and the DHCP server assigns your device all of your IP configuration details. DHCP uses a leasing system to assign these IP addresses, so you are only using this IP address for a certain amount of time, and after that lease expires and you're no longer on the network, that IP address goes back in the pool for someone else to use. Network administrators can also configure DHCP servers to always assign the same IP address to certain devices. So if there are routers, firewalls, switches, and other infrastructure devices on your network administrator may configure DHCP reservations so those devices always receive the same IP address every time they're booted up. This also means that if you need to change any of the IP configurations on these devices, you don't have to go to the devices to make those changes. You simply make them on the DHCP server. The next time that device requests a DHCP address, it will receive the new configuration. If you've ever used a web browser, then you've used HTTP and HTTPS. HTTP is the Hypertext Transfer Protocol, and this is the common protocol used by our browsers to communicate to web servers. There are two different protocols depending on the type of communication that you'll be doing. If you're communicating in the clear or in a non-encrypted form, you would be using the HTTP protocol, which uses TCP and port 80. If your browser's communicating over an encrypted connection, then it's probably using HTTPS, the S being for secure, and that uses TCP port 443. We mentioned earlier that sending email messages can use SMTP, or the Simple Mail Transfer Protocol. But to receive email messages, you would commonly use POP3 or IMAP. POP3 is the Post Office Protocol version 3, and it commonly uses TCP port 110. POP3 was designed to retrieve email messages to an email client, but it wasn't built for multiple email clients. And of course, these days, we tend to walk around with many different mobile devices all accessing the same email inbox. To be able to synchronize across all of these different mailboxes, we commonly use IMAP 4, or the Internet Message Access Protocol version 4. IMAP commonly uses TCP port 143 to be able to download and manage that mailbox. Many operating systems have their own method of transferring files and information between devices using that operating system. Windows commonly uses Server Message Block, or SMB, to be able to provide this connection. This is the protocol commonly used by Microsoft Windows, so if you're transferring files between devices or you're sending a print job to a printer, it's probably using SMB. You might also hear SMB referenced as CIFS, or the Common Internet File System. SMB uses a number of different protocols to be able to communicate. And if you're communicating to an older Windows machine, you're probably using NetBIOS over TCP/IP. NetBIOS is the Network Basic Input-Output System. This uses UDP port 137 as a name service function so that it can find devices on your network by the name, and uses TCP port 139 to set up a session and transfer data between devices. On most modern versions of Windows, NetBIOS isn't used. Devices can communicate directly between each other using TCP/IP. In those cases, it would use a direct SMB connection using TCP port 445. This allows us to have a direct SMB communication between two devices by using only TCP/IP. If you plan on doing any work as a network administrator, you'll become very familiar with SNMP, or the Simple Network Management Protocol. SNMP allows a network management device to query these infrastructure devices for performance details and receive those metrics in return. This uses UDP port 161 to perform these queries. You can also configure the infrastructure device to monitor for certain metrics, and if it exceeds any of those metrics, it can send an alert to the management station. We refer to these alerts as traps, and the traps use UDP port 162. If you're configuring SNMP on a device, it will ask you if you're using version 1, version 2, or version 3. Version 1 was obviously the original SNMP version. It sent structured information across the network, but all of this information was sent in the clear or in a non-encrypted form. We introduced a newer version of SNMP with SNMP version 2, which allowed us to do bulk transfers of information, but still all of that information was being sent in a non-encrypted form. To be able to include additional security with SNMP, you need to use SNMP v3. This includes encryption that allows us to have message integrity, authentication, and encryption of all of the SNMP data. We use directories extensively on our modern networks, and one very common protocol to use to query these directories is LDAP. LDAP is the Lightweight Directory Access Protocol, and it commonly uses TCP port 389. There are many implementations of LDAP, but one of the most popular is Microsoft Active Directory, which allows you to query that Active Directory server using the LDAP protocol. If you've ever worked in a support role or on a help desk, then you've probably performed some type of remote access to someone's desktop. One very popular protocol to provide this remote communication is RDP, or the Remote Desktop Protocol. This is the standard protocol used by Windows for the remote sharing, and it commonly uses TCP port 3389. These remote desktop services are available in many different editions of Windows, and if you're using Windows today, then you probably have built into the operating system the ability to connect to or receive a remote desktop session. RDP can be used to take over and control an entire system or just to run a single application from that server. Although you'll find servers running RDP almost exclusively on Windows, there are clients that you can run on almost any operating system. So if you're running Linux, Mac OS, Android, or any other operating system, there's probably an application you can load that will allow you to connect to a Windows device using the Remote Desktop Protocol.
Hello and welcome to a lesson that will address the key differences between SSL and TLS. This video is intended to provide a high-level overview for those of you studying for the CISSP exam or for those of you in the general public who might just want to know for your own benefit. So without further ado, let's dig into it. SSL stands for Secure Sockets Layer, and TLS stands for Transport Layer Security. Typically, when referring to SSL, the industry is talking about something called SSL 3.0. SSL is an example of what ISC squared used to call hybrid cryptography, which basically means it's a method of using both asymmetric and symmetric cryptography to send secure communications. SSL and TLS are both represented by the padlock icon in your browser when you visit a website. TLS 1.0 and 1.1 are the sequels to SSL. They are basically the same protocol as SSL, but are considered vulnerable. TLS 1.2 and 1.3 are the most recent versions and considered secure. So what are the differences between SSL and TLS? To do that, let's first quickly talk about the similarities. SSL and TLS basically follow the same process. There are some subtle differences, but unless you're working in this field, you probably don't need to know their finer details. For information purposes, there is a client and server handshake process, followed by a key exchange, followed by the encryption of data sent between client and server. If you'd like a little more information on how that process works, we have a separate video that covers asymmetric encryption, so I recommend watching that, where we explain with visuals how the process works. Both protocols can use an algorithm called RSA, or Rivest-Shamir-Adleman, for key exchange. And the terms SSL and TLS certificate mean the same thing. In other words, if you say to someone that you have a TLS certificate or an SSL certificate, it basically means the same thing. These terms are often used interchangeably in the industry. So now let's look at some differences. One of the main differences can be the use of hashing functions. SSL can use older hashing functions such as MD5 or SHA-1, which have been shown to be deprecated due to the ability to produce something called a collision. A collision is when the digest or digital representation is shown to be the same when there are different inputs. If you'd like more information on hashing functions, we have a few videos on hashing, digital signatures, or digital certificates that covers this information with some nice visuals too. Ideally, hashing functions should never produce the same output given any change to the input. TLS uses SHA-256, which is called collision resistance. In other words, you can have an infinite number of inputs that will never produce the same output, at least with today's modern computing power. There are also some differences in the algorithms used for key exchange. We previously mentioned that both SSL and TLS can use RSA. SSL can also use KEA, or key exchange algorithm, which is based on Diffie-Hellman. TLS uses Diffie-Hellman, or DH variations, which are asymmetric algorithms, or PSK, which stands for Pre-Shared Key Protocol. Once the handshake process is complete and a symmetric key is agreed on, SSL uses the Data Encryption Standard, or DES, and the RC4 cipher. TLS uses the much stronger AES, or Advanced Encryption Standard. SSL uses something called a message authentication code, whereas TLS uses a hashed message authentication code. The difference between these two functions and how they're used in SSL versus TLS gets pretty far down into the weeds, so I won't be covering it in this video. The thing to know here is that HMAC is more secure because it uses a secret key in the hashing function that it performs. So what's the bottom line in this lesson? Well, I would say that SSL and TLS are essentially the same thing in a general sense. TLS is the more updated and secure version of SSL. SSL and TLS certificates refer to the same thing. The protocols operate mostly in the same fashion. One thing to keep in mind is that when talking about SSL on your jobs, be sure to ask what version people are using. For example, if you're maintaining a web application and your internal folks are saying, we use SSL, at that point it's important to distinguish whether it's SSL 3.0 or TLS 1.2, because if you're running a public-facing web application, it's essential that you have the more secure version, which is TLS 1.2 and not SSL 3.0. That's it for this lesson. I hope you learned something. Please take a minute to subscribe to our channel and head over to cissprep.net if you're planning to take the CISSP exam. We have a test bank with more than 1,500 realistic questions that are
internet work. That's why pretty much everything in my house has an IP address. My phone, watch, light bulbs, oven, car, my kids, my toilet. Well, not yet.
I really don't like touching the toilet like this.
But what is an IP address and what makes them magic? Let's talk about that. In fact, this is the first episode in a series I'm calling You Suck at Subnetting, because we all kind of suck at subnetting just a little bit, right? And in this series, we're gonna start with, hey, what the junk is an IP address, which we're addressing today. Addressing. And by the end, you'll have Master Chief, Ninja, subnetting skills, whatever you wanna call it. You're gonna be good at subnetting. That's what I'm trying to get across. And in case you don't know, knowing IP addressing and subnetting is like a required skill for everything in IT, like every single job. Networking, ethical hacking, security, cloud, it all involves an IP address, and it all involves delicious subnetting. This video is also part of my CCNA series sponsored by Boson Software. If you want to get your CCNA or your CCNP, two of the best IT certifications in the world, both protocol addresses. They're kind of like phone numbers that we assign to all of our devices. So when my toilet wants to send a message to my Apple Watch letting him know how I'm doing, he totally can, because they have a way to communicate with each other. They have a phone number. Well, kind of. We use phone numbers to text each other, but devices don't. They use IP addresses. And they look a little different, for sure. And we'll talk about how weird they work. But just know that without an IP address, they can't talk. So that's why we give them one. It opens up communication. Not to mention, it gives your devices the ability to connect to the internet. Because don't you want everything to be able to connect to your toilet? Yeah. So now that we know that if a device wants to talk to any other device, it needs an IP address, that means that the device you're watching me on right now, it has an IP address. Because it's talking to YouTube and YouTube's talking back to it. Let's go find your IP address. Whatever you have, we can find it. On Windows, we're gonna launch a thing called CMD, or Command Prompt. Go and search for that and open it. On Mac and Linux, it's gonna be a thing called Terminal. Launch that. And for your phone or any other device, I'll show you here in a second. Here in Windows, one command. Type in ipconfig, all one word, just like that, and hit enter. On Mac and Linux, type in ifconfig, all one word, hit enter. On your phone, go into your settings, jump into your Wi-Fi info, dive deeper into that interface, and you will see, hey, there's an IP address. And looking back at Windows, here is the IP address. You'll know it because it'll say IPv4 address on the side over here. Don't let the V4 confuse you, ignore it for now. Now let's talk about the sucker, the IP address. He looks kind of weird, kind of dorky, technical. He's a mess of numbers separated by dots, 3 dots. So that's already strange by itself, but then we have this guy, and then this guy. What are they doing? Well, they are basically your IP address's best friends. We'll talk more about them here in a bit. But this guy right here is Mr. Subnet Mask. At least that's what he's called in Windows over here. On Mac or Linux, you might see Net Mask, same thing. And then this gal right here is Miss Default Gateway. She also goes by Default Router, or just Router for short. But enough about them. Let's talk about the star of the show, the one we care about, the IP address. Now let's first cover, how in the world did he even get here? How did your device get this number? Who gave it to him? Is it safe? Who gave this to you, device? Actually, that's a legit question. Sometimes you can get a bad IP address. Different video for another time. So how did your device get this IP address? Did it just fall out of the sky? Yeah, kind of, if you're using Wi-Fi. You see, in your homes and in your businesses, we have this thing called a router. It may look familiar. It might be hiding in your closet underneath that sweater you got for Christmas, which, by the way, rescue it. Get that sweater off of him. He has to breathe. It gets hot in there. The router is the Oprah of your IP addresses.
What?
Every time a device connects to your network, she says, here's an IP address, here's an IP address for you, and for you, and for you. Everyone gets an IP address. Now this dark and mysterious magic known as DHCP is why this works. If you want to learn more about that, we'll talk about that later. But essentially, Oprah gives your devices IP addresses. That's what I want your takeaway to be. Write that down. Okay, now looking back at the IP address, let me ask you a question. How is it that I know that your IP address starts with 192.168.1? Like most of you, that is your IP address, right? Creepy. Especially since each of these numbers can be any number between 0 and 255. So your IP address could be 10.3.2.1, or it could even be 1.2.3.4. So why is it that most of your IP addresses start with 192.168.1? Well, there's a lot of reasons actually that I'm not gonna go into because it does get pretty complicated, but the short and easy answer is that it's Oprah. Oprah decided that that's what your IP address should be. Should start with. It always comes back to Oprah. And the way that Oprah tells us that each IP address in your network, in your house, is going to start with 192.168.1 is through Mr. Subnet Mask. I told you he'd come into play here in a bit. Here he is. He looks even weirder than the IP address. And honestly, he's a pretty complex dude. We're gonna spend a lot of time getting to know this guy in this series. But real quick, can I show you a hack that's gonna save you like 1 billion hours? Now notice that Mr. Subnet Mask does look pretty similar to the IP address. He's got 4 sets of numbers and 3 dots. And if you assume that the first number in the IP address matches up to the first number in the subnet mask, You'd be exactly right. In fact, they all match up. 2 to 2, 3 to 3, 4 to 4. Now here comes the hack. When you see a 255 in an octet, which by the way, each of these sections separated by a dot, we call them octets. We will dive deeper into why we call them that, and yeah, it's gonna get a lot more nerdy and so much more fun. I can't tell you more. Just know they're called octets for now. Just calm down. So anyways, back to the hack. If that number is a 255, then we know that the corresponding number or the corresponding octet will always stay the same. Within your network, that is. So looking at our subnet mask here, we know the first 3 octets, or the first 3 numbers, are 255, which tells us that the first 3 numbers in our IP address, 192, 168, and 1, will always stay the same in our network. We can confidently say that every single device in your network, at your house or your business, if they look like this, they're gonna start with 192.168.1. And that brings us to the last number over here, the 0. What's this guy doing? This 0 is telling us that, hey, this last number, it can be whatever you want, whatever your heart's desire, as long as it's between 0 and 255, but still, whatever you want. You can use them all. So to sum it up, when you see a 255, that number's locked in. These numbers will never change. But the 0 tells us the final number totally will, based on what device it's assigned to. So if you allow me to get a bit nerdier and go a bit deeper, in the networking world, we refer to these numbers right here as the network portion of the IP address. And then on this side, the side that'll change based on what device it's assigned to, we call that the host portion. Because in networking and IT in general, when we have devices on a network, your phone, your watch, your toilet, we call those hosts. Your toilet is a host and it has an IP address. Now what I just explained, put that in your pocket, don't let nobody hack it. This will become very, very important later. But now let me ask you a question. Why is it important that we have to know the network portion of the IP address? Why do we have to know that the IP addresses in our network start with 192.168.1? Analogy time. We can also think about an IP address like the address of our house, like, you know, the place you live. And tell you what, why don't you comment below your home address? No, I'm totally kidding. Don't do that. Are you crazy? Don't do that. But anyways, you live in a house, and that house, most of the time, I think always, is going to be on a street, right? And let's say your street that you live on is Privet Drive. If you know where that's from, comment below. And because you're probably not the only house on Privet Drive, you can't just say, hey, send me a package on Privet Drive. I live on Privet Drive. Oh, houses need windows. I knew it looked kind of weird. Hold on, let me draw some windows. So anyways, we'll assign a unique house number to you. So you might live at 4 Privet Drive, and your buddy might live at 5, and then 6, and then 7, 8, 9, you got it, right? So if I were to send you some network chuck coffee, it would go to 4 Privet Drive. So I sent you some coffee and it was so stinking dang delicious that you wanted to bring some over to your friend, your buddy, Bernard, over at 6 Privet Drive. There's Bernard. Now hang tight, here's where the analogy comes into play with IP addresses. So would you call UPS and say, hey, I have some coffee I want to give Bernard, come pick it up and take it to Bernard? No, why would you do that? Bernard lives on your same street. So as you're preparing to send Bernard some coffee, you would go, hey, Bernard lives on Privet Drive. Therefore, I can just walk outside and hand it to him. Because we're so stinking close, we're in the same street, we're in the same neighborhood. So if you're tracking with me here, this analogy feels weird. I don't know why. Is it me? It's probably me. If you're tracking with me, the network portion of our IP address, the thing that stays the same, is akin to Privet Drive. And the host portion, the thing that does change, is the house address, the house number, 4. Or it could be 5, or it could be 6, based on who you're sending it to. With our devices in our network, it's the same thing. If you want to share a picture from your phone to your computer, your phone will look at the IP address of the computer and go, oh, hey, yo, we're on the same network. 192.168.1, he's in my, and my laptop will go, dude, he's not in my network, he's not in my same neighborhood, I need some help. I need to call UPS. Except in this scenario, it's not UPS, it's Miss Default Gateway, or Miss Default Router, AKA router. Your computer or any device on your network will look at its IP address and then look at Mr. Subnet Mask and go, huh, my network is 192.168.1, Netflix is not in my neighborhood, I need help, please help me, Miss Default Gateway. Miss Default Gateway, she knows everything. She knows exactly how to get to Netflix and she'll take it from there. Now fun fact, Miss Default Gateway, she's actually your router. She's Oprah. I know, mind blown the entire time. Never saw it coming. What a plot twist. That's some Scooby-Doo stuff right there. So to sum that part up, whenever any device in your network, whether it's your home network or a network at a business or pretty much any network in the world, when it wants to talk to something not on its same street, when it wants to talk to something outside its network, it has to talk to its router, its default gateway, to get out. It has to talk to Oprah. Write that down. Now real quick, I got a challenge question for you. Let's see if you've been paying attention. Looking at my network here, which might be the exact same as your network, I told you this is one of the most common networks in the world. Or did I tell you that? By the way, this is one of the most common networks in the world, my kid just screamed, for private networks. Looking at this IP address and looking at this subnet mask, how many possible IP addresses are available to assign to devices in your network? And by the way, if you can figure this out, that pretty much covers the majority of networks. I'm not sure what the statistics are, but I think, like, Network Chuck's opinion, like 95% of all networks kind of look like this. So go ahead and comment your answer below, just raw without me telling you. I'm curious what it will be, but let's walk through it real quick. And you're probably wrong. Sorry. Looking at this, we know 255 in the subnet mask means this number locked in stays the same. So does this one and this one because of the 255. But over here is 0. We know this last number can be anything as long as it's between 0 and 255, which would give us a total, including 0, of 256 IP addresses. Party, we got a ton, but you're wrong. It's not 256. Because like everything in life, there's a catch. There's always tax, there's always extra fees. You always have to look for that. Life lesson. Anyways, here we go. Where's the catch? Where's the extra fees in our networking? Well, first of all, right off the bat, there are always 2 IP addresses that are reserved, that you cannot touch, you cannot use in any given network. First, it's the first IP address in your network. So in this one, it would be 192.168.1.0. That one's untouchable. It's referred to as the network address. He's a leader, he's the firstborn son, you can't touch him. The second IP address you can't touch is the last IP address in your network. In this particular network we're talking about, it'd be 192.168.1.255. This guy, dude, he talks way too much. He's a chatty Cathy. We call him the broadcast address because when you tell him something, he tells it to everyone. Can't keep a secret. That's legit what he does. When you send anything to a broadcast address, the last IP address in a network, it literally will broadcast it out to everybody. It's like, hey, everyone, guess what? So don't tell him anything unless you want everyone to know. So that's 2 you can't touch, and then 1 you really have to think about, and it might just be Miss Default Gateway. There has to be a router. Oh, I just drew over that. There has to be a router in your network, and that will take up 1 IP address. So we're now 3 IP addresses shy of 256, which gives us a total of 253 usable IP addresses. If you got that right, you're on your way to becoming a subnetting master. Congrats. If you didn't, that's totally okay. This is so brand new and can be very complex. But don't worry, we're gonna hold hands. No, I'm gonna hold your hand and walk you through this. So, little coffee break. We covered so much in this video. Oh, that's cold coffee. Yeah, that's how long I've been here recording. It's cold coffee. Like the video because I just sipped some cold coffee and I need to go heat it up. But anyways, let's take a look at what we covered so far in this video. We talked about IP addresses, right? We talked about that everything in your network, in your house, that wants to connect and talk, either to other devices in your network or to devices outside the network on the internet, Netflix, or just your toilet having a conversation with your watch. If any of that needs to happen, you have to have an IP address. Basically the cell phone number of your devices. Unless you actually have a cell phone, then it also has a cell phone number and an IP address. Very confusing, I know. Chuck, get better at analogies. You also get a chance to meet Mr. Subnet Mask, a very complex and mysterious dude you'll get to know a lot better in the coming videos. He also goes by NetMask, and he tells us and our devices what our IP addresses in our entire network start with. He tells us what street we live on. In this network right here, the street we live on is 192.168.1 because of our little hack, the 255s. And then finally, you met Miss Default Gateway, aka Default Router, or Oprah. She does it all. Not only does she give all your devices in your network an IP address, but she can help you get outside your network if you want to go visit Netflix or networkchuck.com or even better, networkchuck.coffee. So anyways, that's IP addresses. And I just realized I spelled IP address wrong. Let's add the extra D. Cool, we're good. And let me tell you, yes, we are just scratching the surface. We're gonna get much more complex on how IP addresses work in the world and in your home network and in your business. And you'll learn that killer skill, that crazy awesome skill that you pretty much need for anything in IT, subnetting. Because let me tell you, this example we've been working with here is very, very simple, but don't you worry. You're gonna learn the skills to make this crazy complex and fun. And by the end, you will be a Master Chief Ninja Subnetting Master. Did I say master twice? That's fine. This video is sponsored by Manscaped. Hold on. IP address, and this particular network is smaller with 256 addresses. So they can take their big, massive network and turn it into smaller subnetworks. And that, my friends, is your first little glance into subnetting, which is what we're gonna really cover and dive deep into in the coming videos. Oh, and by the way, also, what we did here, taking a Class A network, and we cut it up and made it smaller with a different subnet mask other than its default. We call that a classless network. So for example, my home network is actually 10.7.1.0, a Class A IP address or a Class A network, but my subnet mask is 255.255.255.0, making it a degenerate, a classless network, because we're breaking all the rules. We're not obeying this A, B, C, D, E, F, G stuff. That's basically what you're doing. Got no class. But if you do obey the rules and you use the default subnet mask, then you're class full. You're full of class. You're elegant, but you're no fun. No, I'm just kidding. A little bit. So anyways, getting back to our address ranges, our classes. We focused a lot on Class A right here, and his subnet mask giving a network just a ton of IP addresses, too many. Way too many, which is, again, is part of the problem I have with IANA, or the head Oprah. They just gave away too many IP addresses. And then as we move down, you'll notice that Class B has a different default subnet mask of 255.255.0.0. So again, if we take this first network right here, bring it on down here, it might look like this with a subnet mask of 255.255.0.0. Locking in those first two numbers, those first two octets, those will always stay the same. But then these last two numbers, these last two octets can be anything they want between 0 and 255. I'm talking 65,534 hosts or IP addresses per network. So bummer, you get less IP addresses, which again is way too many, but the flip side is that you get more networks with a Class B. IANA, or Queen Oprah, can assign 16,382 networks, because again, a Class B, by default, must have a minimum of a subnet mask like this. And then moving on down the line, we got Class C, which will look the most familiar to you, right? Because it contains your home network. And again, we'll take that first network here, bring it on over here, come on little guy, with this default subnet mask. And those first three numbers, they're locked in. Can't touch those octets. And looking very familiar, we have a total of 254 available IP addresses on that network. This is the best plan. They should have done this with every single network, because with Class C networks, we have a total available for Queen Oprah to assign 2,097,150 networks. So if they had done that with every class, we'd be okay. Kind of, maybe. No, we wouldn't. We have a different solution for that, because eventually we would have run out. But we wouldn't have run out so quickly. Come on. Inventors of the internet, why can't you just look into the future and anticipate our needs? Seriously. So that's Class A, B, and C. We're about to get to the D and E, which infuriate me. I mean, I don't get too angry about it, but it's still pretty stupid. But first, I just want to point out, and hope that you're picking up, that the job of the subnet mask is to help us determine how many networks and how many hosts we have for each class. Class C gives us the most networks and smaller hosts per network, whereas Class A gives us too many freaking hosts per network and like only 126 networks if you stuck with the, classful subnetting or classful networks. But of course, and you probably assume this, nowadays, we mainly do classless networks to take advantage of the IP addresses we need to use. So anyways, I'm gonna officially say, IANA, that was a dumb idea. And now we're stuck with your mistake. But it's okay. All we have to worry about is learning this chart, memorizing it, knowing what it is, and then learning something scary called IPv6. We'll cover that later. So now let's talk about my biggest problem with this, is that there are IP addresses that we cannot use. We just can't. We can't. So Class D and E, notice they don't have a subnet mask because it doesn't matter. Class D IP addresses are reserved for multicast, or you might see it written in one word. I never know. All you have to know about those is that they're very important to networking and you can't use them right now. So don't worry about it. Just memorize what they are. And then Class E networks, these bad boys are mysterious. They are locked up in the Department of Mysteries, FBI, CIA, I don't know. They are experimental. So don't even think about touching those. Whew, you'll get in trouble. And I'm just kidding. You can't touch them. They're untouchable. Anyways, so we can't use D and E. And there's one more. I don't know if you noticed this. Look at that chart. Is there a number range missing? Can you find where's Waldo? I'll give you a hint. It's in between A and B. And also, here's the other hint, Dorothy, because there's no place like home. This will make sense. I promise it'll make sense here in a bit. I'm not losing my mind. You may have noticed that the range here ends at 126 and then picks back up in B at 128, making us go, huh, where the junk is 127? Like, where'd it go? That's a lot of IP addresses just missing. That's an entire Class A network, which means we're talking 127.0.0.0 with the subnet mask 255.0.0.0, which leaves missing over 16 million addresses. Where are you guys at? You know where they are? They're on your devices. These range of addresses, anything beginning with 127, are what's known as loopback addresses. You may have heard that term before. They're used for network testing. Now don't get me wrong, I love me a good loopback address because you can use it to test your network. You can actually make sure that your computer's networking is working by pinging your loopback address. What am I talking about? Let's try it real quick. If you're on Windows, go ahead and launch your command prompt or type in Windows key search CMD. It'll look like this. On Mac and Linux, it'll be terminal. And right here, stand across the board, type in PING or ping space 127.0.0.1. Now, if you're like, what the junk is ping? Ping is what we use in IT to see if something is alive and awake. So for example, I, on my computer, might send a ping message out to networkchuck.com saying, hey, are you awake? And if networkchuck.com is awake and alive and actually there and living, he should respond back with a response. It is by far the most common troubleshooting tool you'll ever use in IT. So looking back at our example here, we're gonna ping 127.0.0.1, which is an IP address that just is virtual and lives on your computer. And we should all get the same result if you're working. Hit enter. Hey, are you awake? Yes, I'm awake. Hey, are you awake? Yes, I'm awake. That's essentially what you're doing. You're just making sure that you can hear yourself. But the kicker is, and it's so stinking stupid. Maybe, is there something I don't know about this? Here's the problem. I think all we needed was just this one IP address, 127.0.0.1, to test our NIC, our network, to make sure it's working, because we just did that. But for some reason, they thought we might need 16 million to do that. Because, do this. You can go ping 127.145.145.8. Just a random address, and we get the same thing. We're pinging ourselves. Our computer has 16 million virtual IP addresses ready to respond to itself. Why? Okay, it's okay, Chuck, it's okay. So, roughly 4.3 billion IP addresses. And we can't use a lot of them. And a lot of them were mismanaged. Thanks a lot, Ayanna. Thanks a lot, Head Oprah. No, it's fine. It's fun to learn this. It's fun to learn how our IP addresses were formed, how they're organized into classes A, B, C, D, E. And it's definitely something. It's 1990.